So, Dr. Sundar, if you can please share your screen.
Yeah, 1 second.
Yeah, it is fine. Okay, so Dr. Sundar, I'll take 2 minutes to introduce you to our audience, and then it'll be over to you. Okay.
Sure. Yeah.
So, welcome everyone. I am honored to introduce our guest speaker for today, Dr. Sundararajan Natarajan. He received his PhD from Cardiff University, Wales, UK in 2011. He is the recipient of Zinkiewicz Best PhD Thesis Award from Association of Computational Mechanics, UK. He was a postdoctoral researcher at Indian Institute of Science, Bangalore between 2011 to 2012, and he was a university postdoctoral fellow at the University of New South Wales, Sydney, Australia between 2012 to 2014. He joined Department of Mechanical Engineering, IIT Madras in 2014, and he is now an associate professor at IIT Madras in the Department of Mechanical Engineering. His research interests include computational mechanics for moving boundary problems, advanced discretization techniques, and multiphysics problems. So let us welcome our speaker for today, Dr. Sundararajan Natarajan. Over to you, Dr. Sundar.
All right. Thank you. Good afternoon, everyone. Thank you, Gaurav, for the nice introduction and giving me an opportunity to talk about some of the research work that I'm doing here at IIT Madras. So the topic I've chosen for today's lecture is advances in computational mechanics. I believe the audience here are familiar or have undergone a course on finite element methods. So this is slightly an advanced topic, the finite element method. Here, what I plan to do is give you a very brief overview of different techniques that people are working on, which are an improvement to finite element method. So I'm not going to show any results or nice animation, but to expose you, to give you an idea of what the current trend is in terms of computational mechanics that people are working on. Yeah. So if you have any questions, you can stop me in between. So the outline of my today's talk is start with the motivation, give you a quick overview or background on computational mechanics, refresh our idea on Galerkin framework, talk about some of the difficulties and disadvantages that the conventional finite element method has, and then look at different advancements that people have done to improve finite element method, right? So some of the things that I would talk today would be on polygonal finite element, extended finite element, isogeometric analysis, scale boundary finite element method, and smooth finite element method, and conclude my talk with a very brief summary. So one thing that you might think, why do we have so many different methods? And I believe by end of this talk, you will understand that although we have many variations or advancements in finite element method, they all can come under the big umbrella called the Galerkin finite element framework, right? So all these are not completely different from finite elements. They still work with the same idea of what Galerkin proposed, except that it adds additional features to conventional finite element method. So computational mechanics, as we know, has revolutionized the way we do design, do stress analysis, the way we do understand things. That could be attributed to the fact that the computer hardware and software has tremendously increased over the last decade. So now we are able to leverage those power and to solve interesting problems using finite element method or in the numerical method in very generic area. And so the other advantage is that it can probe into areas that theoretical and or experimental investigations are too difficult, right? So of course, when finite element or numerical methods were introduced, people had a notion that it's going to completely stop experimentalists from it's going to put all the experimentalists out of work. But that is completely not true, because it's going to only help experiments or experimentalists understand certain things better or help theoreticians, right? You might have heard this saying, garbage in, garbage out, especially for finite element methods. So it depends on what we give it as an input. The output will depend on how good the input is. So there are some things that we can do with finite element method or numerical techniques, which can otherwise it's not possible with the experiment. Right? For example, if you're trying to solve elasticity problem, and if you want to study the role of Poisson's ratio, what does it, how does it impact? We can just arbitrarily set Poisson's ratio to 0, which could be a hypothetical material, or there could be no material with a Poisson's ratio 0. But a numerical framework could allow you to understand the implication of having a Poisson's ratio 0 or greater than 0, which can then help us understand or design new materials which can have superior properties for certain applications. And what I believe is that theoreticians, experimentalists, and numerical analysis have to work together for better understanding of things around us, for improving the design, in having new materials for different applications. And with the buzzword of data, being around, I think instead of 3 pillars, I think the 4th pillar would be the data analytics, which have to be worked in unison with the other 3 for improved design. So let's look at what is the philosophy behind the modeling and simulation and how it works. So we have a physical problem, and seldom this physical problem can be understood. So we convert the physical problem into a mathematical problem. This could be in terms of ordinary differential equations or partial differential equations, or it could be just simple linear equations or nonlinear equations. And the solution of this equation will give us an indication of how the physical problem responds to a particular situation. But again, many times solving this mathematical model is out of reach. So we resort to numerical methods, which relies on so-called discretization. So discretization could be in space and in time, right? So you can have a temporal discretization and a spatial discretization, which essentially converts the differential equation, which is in a continuous form, to a system of linear equations, which can then be solved using computers. So if you look at the irony here, that the physical problem is discrete in nature, and then we put together the mathematical model to it, which converts the discrete form to a continuous form. But we're not able to solve the continuous form, so we again go back to a discrete form by using numerical techniques. Just to a side note, people are now looking at ways by which you can go from the physical problem directly to a discretization without having to introduce a continuous form. So you still need a mathematical model, but the mathematical model would now be a discrete model rather than a continuous model. Anyway, so once you have the discretization, it basically converts the differential equation to algebraic equation, and then we can use the knowledge of linear algebra to solve for the solution. So this is typically the flow as to how we go and understand how a physical system works. However, in this whole process, we know that we have to do a lot of assumptions and approximations in going from one step to the other. For example, idealizing a physical problem to a mathematical problem, we introduce what is called as a model error. And when converting the mathematical model to a discretization, we introduce what is called a discretization error. And the last one is when we try to solve the system of equations that we get by using these approaches, using a computer, we end up doing what is called as a numerical error. So the total error that we would get at the end is a combination of the model error, discretization, and numerical error. Right? So it's very important that we understand the errors that come at different stages so that we can minimize a total error. In principle, then we'll be able to address or solve the original problem. So there are different things, when we talk about the model error, the first question is, are we solving the right problem? In the sense, if you have, let's say, a brick structure and then you have idealized that, let's say, a plate problem, then that could be a valid assumption, as opposed to if you are trying to model that as an axisymmetric problem, which is really not the case. Once you have validated, then the question is, are we solving the right problem? In a sense, and that's called the verification stage, which mostly is related to the way we discretize. It could be the space or the time, and the way we use algorithms to solve these system of linear equations. And recently, the question is, can we solve the problem fast enough? So with increasing computing power, we are, our handsets, mobile handsets are about 8 GB RAM now. So the question that we are trying to ask is, how fast can I solve the same problem, so that we can reduce the overall computational effort and probably the design time in the whole process. So put together, there is one thing called a model reduction error, where people work on, where they try to improve the way the physical problem is represented using a mathematical model. For example, if a physical system is anisotropic in nature, and if you try to use an isotropic material model, that introduces what is called a model error. And now, to reduce it, we might have to improve the constitutive model. So that area would be related to model reduction error. The other error is related to how we can improve or how we can reduce the error that comes from discretization and the numerical error, which is grossly termed as a model reduction error. And in this talk, we will focus mostly on the second part, where we try to understand how the finite element method that is in practice can be improved to solve a variety of problems. So we assume that the physical problem or the mathematical model that is given to us, first of all, it's unique, it has solution, and now we try to come up with a way to solve these problems in an efficient way. So the talk is going to be focused more on the verification rather than on the validation. So just to give you a quick overview of what the Gaussian method is, let's look at a standard elasticity problem. Ignoring body load and inertia, the governing equation is given by this equation del dot sigma equal to 0, which is called the strong form, and this is a partial differential equation. This is supplemented with a set of boundary conditions. Some of them are essential, some of them are natural boundary conditions. So the essential boundary conditions are on the displacement, and the natural boundary conditions are on the surface. Right? And we also assume that the body has some internal discontinuity. That discontinuity could be a crack or could be a material interface, over which some traction can be applied. The governing equation is in terms of stresses, which doesn't have enough number of equations to solve for the unknowns. So what we do is traditionally we invoke the strain displacement relationship and the constitutive law to convert the differential equation in stresses to differential equation in terms of displacement, which will then give you enough equations for the number of unknowns that we have, so that we can get a unique solution. Of course, this all put together is what is called the strong form. And in numerical approaches, we convert the strong form into what is called as a weak form, where we use Lyapunov-Galerkin type approach, where we construct or take test and trial function space which satisfy the boundary condition, and by invoking Gauss divergence theorem, we convert the strong form into the weak form. So I'm not going to the detail of all these techniques, because I believe you have gone through this in your finite element lecture. So put it simply, the weak form now reads as a fine displacement, which is a function of some polynomial space, such that the bilinear form is satisfied. Bilinear form is basically AU comma V equal to L of V. In other words, the bilinear form gives you KU equal to F, which is the system of linear equation, if we have started with linear system of equation. In simple words, what we're trying to do is we are trying to convert the problem into a discrete problem by dividing it into non-overlapping regions called elements. And then we try to approximate the solution over each of these elements, and the summation of all those is what is going to give us a rough approximate of the solution over this entire domain. Right? And in 2 dimensions, the typical discretization is relying on dividing the region into triangles or quadrilaterals. And in 3 dimensions, they can be divided into tetrahedrons and hexahedrons. So this is the typical setting for a finite element framework. And if you look at the design perspective, the conventional design process would have 3 steps. One is the CAD model, which is typically written in terms of possibly non-uniform rational B-spline. But this is not analysis suitable yet, right? Because with finite elements or any other technique, you would want to discretize the space into smaller regions. We call that to be analysis suitable model. And many times, this discretization, also called as meshing, is the most expensive part of the entire process. But once you have the discretization done for the problem, for the domain, then we can invoke one of the analysis techniques that is available to us to compute the necessary information. So it could be the first natural frequency, or it could be the mode shape, it could be the stresses, strains, the displacements, and things like that. Yeah. And if it doesn't meet the design requirements, you go back and fix the CAD model, and then this process continues over and over again. And every time the CAD changes, the mesh has to be updated, which again, if it is the most expensive part, that's going to completely increase the turnaround time for the design process. Right? So we will see how people have come up with unique ways to address this issue. Although finite element is very robust, there are certain difficulties or challenges it has, as with any numerical technique. So things that we have to keep in mind is that we are trying to find an approximate solution, and there is always room for improvement, in the sense that approximation techniques have some assumptions, right? And if we can relax certain assumptions or the constraints that a particular numerical technique put forth, we can achieve a better approximation. That's the whole idea, right? So remember, we talked about dividing the domain into smaller elements, typically triangles or quadrilaterals in 2 dimensions. So finite element requires that these elements have nice shape, and there has to be some regularity condition that has to be met. Otherwise, the solutions are really bad. So care has to be taken in having a nice quality element. So the element shape has to satisfy certain conditions. Although we may start with a good quality element, but if you are going through, let's say, large deformation problems, there could be cases or region times where the elements get really bad shape, as you see here in the top right corner, which would stop you from further proceeding with analysis because the element does not meet the element shape criteria. So one possible solution to be is to stop the analysis, do the remeshing locally, update the variables, and then continue the analysis. Again, every time you stop and update the mesh, you're going to increase the computational time. Finite element method in its original form requires that the mesh has to conform to the geometry, and that we use polynomials to approximate the unknown field. So these two really are a constraint if you're trying to solve certain class of problems. For example, if you're trying to solve a problem where you have a strong a steep gradient, right? For example, what I've shown here is a case where there is a geometric discontinuity, and because of which this point experiences a very large gradient. And simple polynomial cannot actually represent this gradient very accurately. So what we do is we have to use extremely refined mesh closer to the region. And that again increases the computational effort. Think of the case if this sort of singularity or the gradient moves or evolves in time over this domain, so which implies the mesh has to be updated. So one thing that would probably come to your mind when I talk about moving gradients is, a typical example is the crack problem, which we were seeing in this talk today. And because it requires a conforming mesh, generating a conforming mesh is also not that trivial, right? And with a reasonable time with a good quality mesh. For example, if I'm trying to solve or understand what is happening in, let's say, a polycrystalline material, where for argument's sake, let's say that dark black lines represent the grain boundaries, and each of them are grains. You can see that the mesh, first of all, has to conform to these grain boundaries. And now, because of different physics, there could be something happening at the grain boundary. Cracks can start evolving. It's not that easy to work with finite elements there, right? And since these polycrystal materials have different elastic modulus, our knowledge on elasticity tells us that the points where these grains intersect are the likely sources of high stress concentrations. And high stress concentrations are the points where it's likely to start a damage to evolve. The damage can then become a crack, and then it really becomes computational intensive if you use numerical technique to solve. So the last of the difficulties, there are other challenges, but the last of the difficulties that we want to highlight here is a geometric representation error. Remember, we had a picture of a circle. We divided the circle into small triangles. And we know that by dividing into triangles, we are only approximating the circumference of circle, because the triangle cannot exactly represent the curvature of the circle. Of course, one way would be to use extremely refined mesh and hope in the limit that the length of the side of the triangle is as small so that we can approximate the curvature. The moment you start increasing the number of elements, you're also increasing the computational time that is required to find the solution, right? So if you increase the number of unknowns, the number of equations that you have to solve also increases. That becomes a load on the computer. And again, people have been thinking about this, and there are techniques by which you can actually address these issues. The reason why I have taken some of these setbacks is that the methods that I'm going to talk today are somehow related to these approaches, yeah, these setbacks. Okay, so before we talk about different methods, so here is one difficulty with finite elements that I would like to emphasize here. So here you see there are two situations. The one on the left, you have a domain, and then there is you start with a small circle, and then the circle becomes an ellipse, and it changes time. With time, it changes shape, and you can see that every time the inner geometry changes, the mesh has to be updated and adapted, which could be really complicated if you have multiple sources, or if it changes the topology every time. The one on the right you see is a classical example of a crack growth problem, where the solid red line is a crack, and since crack within linear fracture mechanics has a singularity at the crack tip, you need to have an extremely refined mesh close to the crack tip, and every time the crack moves, the mesh has to be updated, right? So think of a situation where you have like 100 cracks, and then you want to evolve all of them together, and that's really computationally intensive and cumbersome task, right? So we will see some of the techniques that have been evolved to address these issues. Okay, so what I've done on this slide is put together, based on my understanding, into the methods into 4 different baskets, right? So the first one I call as improving element formulation. The second basket is decoupling geometry and analysis. The third basket is boundary discretization. And the last one is counterintuitive to the second basket, where we said we are decoupling, but here we are seamlessly coupling the geometry and analysis. And the problems with finite elements is not a new concept. People have realized this as early as 1960s, 70s. And since then, people have been trying to improve the method. For example, the earliest you could probably think of is the mesh-free methods that people started to work on as early as 1977. Polygonal finite elements as early as 1969. Boundary discretization method, where you have boundary element method, 1967. Very recently, scale boundary finite element method, early 2000, right? And smooth finite element method, very recently, in early 2000. Isogeometric analysis, where we try to couple the geometry analysis, introduced by Tom Hughes in 2005. But if you look at from a bigger perspective, all these are Galerkin framework, except for this basket, which is a boundary discretization. The other three are based on domain discretization. In the sense, you can have a single framework, but by changing the way we write the approximation functions, we can get different methods, right? So this is something that I emphasize in the class when I teach finite element method, is that the real hard work or the genius is Galerkin, because he said the way to solve the differential equation is to approximate them. And one way to approximate them is to write it as a linear combination of functions. So that's all he said, right? Because we choose simple polynomials for ease of working with as we can easily work with polynomials, but that doesn't really stop us from using complex functions. So all we have done now is to now explore the possibility of different functions that we can use it to approximate the unknown field. That leads us to a different method, sometimes with improved property. For example, if I use a moving least square approximant within the Galerkin framework, what we end up is getting a mesh-free method. And if I use, let's say, non-uniform rational B-spline as an approximating function, I end up with what is called as the isogeometric analysis. So they're all the same, except that we, slightly use a different set of basis function to approximate the unknown field. So what I'm going to talk today, or give you a quick overview of the methods that I've highlighted here: the smooth finite element method, polynomial finite element method. I'll quickly touch upon partition field enrichment, scale boundary finite element method, and isogeometric analysis. Again, like I said, I'm not going to show you any results, but give you an idea of how it works. For results, you can always write to me to discuss further, or look at the papers that are available in the literature. Any questions so far? I hope I'm still online.
Yes, Dr. Sundar, we will take the question from the participants in the end.
And okay, fine.
Yeah.
Right. So the first I would like to talk about is on polygonal finite element method, where the idea is to relax the element topology. Remember, when we talked about finite element method, the first we said the domain has to be discretized only using triangles or quadrilaterals. Because if you think of it, that really is not a constraint. We could probably discretize using any arbitrary element. But then the constraint actually came from the fact that we write unknown field as certain functions, and these functions were defined only on certain geometrical shapes and only on a specific space. For example, we call that to be the isoparametric space. Now here with this rational thinking, we can now allow the domain to be discretized with arbitrary polygons, right? So you will see that in the next couple of slides. So this is to give you an idea. So you have a domain of interest. Conventionally, we divide that into triangles. Of course, we can also use quadrilaterals. Typically, we just use triangles to do it. But what we want to do is this the only constraint, or can I use some other element, right? So the answer is yes, we could use polygonal elements, and the reason could be from the calculus, or from the local meshing, or from the use of transition elements, right? So if you look at the ways, one of the ways by which you can generate a triangular mesh is to do what is called as a Voronoi tessellation, or you divide that into region of polygon, and then by connecting the center of the polygon, we get the triangular mesh. Yeah. So now the question is, that's a two-step process to get a conforming mesh to be used within finite element method. So the question people ask is, can we stop at the point where we generate these polygons? Can I use the polygon as an element itself, right? So that's from the calculus consideration. And if you look at the meshing perspective, there could be regions where you have pi-sided region, and then you want to use finite elements. The only way to do it would be to either use a quadrilateral and a triangle, or a combination of triangles, right? And remember, we talked about the elements should have a proper shape. You'll see that this small triangle is next to the larger triangle, which may affect the final accuracy. So the question is, can I now treat this pi-sided element, pi-sided region as an element itself? So that's from the local perspective, meshing perspective. There could be regions where you need a highly refined mesh, but then there could be regions where you don't want a refined mesh. You would want to have a coarsened mesh. Typically, what we can do is we use transition elements. So these transition elements typically are triangulated to avoid incompatibility issues. So the question is, can I have elements which can have arbitrary number of nodes on the boundary? For example, this typically is a four-sided element, but with an additional node on one of the sides, and this is additional nodes on the two of the other sides. So the question is, can I now, without triangulating it, can I use this as a polygonal element with 5 sides, a polygonal element with 6 sides, right? So, and that is now possible. So now, if you have a domain of interest that can be converted into regions of polygons, and there are different approaches by which these polygons can be used within finite element framework. So one is a traditional polygonal finite element method. We have what is called as a scale boundary finite element method and virtual finite element method. So all these approximations try to get the stiffness matrix and mass and force vector, which are essential in converting the differential equation into system of algebraic equations. So applications of these polygonal elements, it's really easy to divide or discretize the domain into polygons as opposed to triangles or quadrilaterals. One of the hypotheses is that if I want to analyze a polycrystalline material, typically what we do is we take each of these grains, all these colored regions could represent a grain, and these grains are further divided into smaller triangles. Yeah, because we cannot. So now hypothesis is that, can I use this one grain as one big element? And then, if that being the case, then I could use a larger RVE or representative volume element, which can solve the problem. And polygonal elements, finite elements are heavily used in computer graphic applications. This is my favorite application, which I inform in the class. So this is a character from the movie Incredibles Part 1, where this is the character, this is the boy who runs on the water, and that movie heavily used polygonal finite element method to animate the characters in the movie. And since then, all the animated movies have some essence of mechanics and computational mechanics, by which they can animate these characters. So they bring in physics. They also bring in new techniques from computational mechanics to to animate the character. So these techniques are not just used for solving elasticity equations, but also to have some fun moving characters in the animated movie. Okay, so that having polygonal elements is from the meshing perspective. So now I can have a routine by which I can divide the region into polygons. But to be able to use within finite element method, we need to write what is called as a shape functions over these polygons. And we know that the shape functions over a particular element has to satisfy certain properties. One of them is they should be non-negative. They should be linearly complete. The most important property is that they should satisfy partition of unity. They should have linear precision and preferably interpolation, right? Interestingly, what happens is that if I write the shape functions over polygons, it happens that it is not unique. The shape functions over a triangle is unique, but not over polygons, right? That has led to different approaches by which you can write the shape functions over polygons, and all these are collectively called as barycentric coordinates. So here I've listed few of the approaches that are available to write the basis functions over polygons. Sorry. As you can see, people have started to think about this as early as 1975. Washburn was the first one to introduce a systematic procedure by which you can write shape functions which satisfy the partition affinity over arbitrary polygons. And that got momentum in early 80s, and since 2000, it has really picked up. With the advent of computer graphics and people from computational mechanics also trying to use these elements, it has really got into momentum. And there are different ways by which you can write these basis functions that collectively satisfy all the properties that we just saw. So here I would just like to quickly touch upon one particular way by which you can write the basis function is by harmonic functions. So harmonic functions or harmonic coordinates it's very easy to visualize. They can be obtained by solving a Laplace equation on any particular region with certain boundary conditions. Right. So let's say that I would want to develop a six-sided element, right? And this element has to have shape functions. In this case, it will have six shape functions. And the property of the shape function would be that if I'm writing the shape function for node j, it should be 1 here. It should be 0 on all other vertices and 0 on the vertices that does not connect to the vertex j. This can be interestingly obtained by solving a Laplace equation with the same boundary condition, right? And of course, you may ask, then this becomes finite element problem. Yes, that becomes a finite element problem. But once you have this library written, you save it in a function. You can now treat this as one big element as opposed to having many elements within it, which drastically reduces the computational effort. This can also be applied in. I'll come back to that. So this can also be applied in 3 dimensions, which I'll show in the later slide. I thought I had it in the next slide. So one difficulty with polynomial finite element method is that we don't have a numerical integration rule to integrate the essential matrices, right? So, and one straightforward or brute force way is to divide the polygons into triangles and use the quadrature rule on triangles to integrate over the polygons, right? The division of polygons into triangles does not introduce any additional degrees of freedom. You should keep that in mind. It is just to get the integration point. So once the integration points are located, these triangles are thrown away, and we just directly use these integration points to compute the essential matrix. So there are different approaches by which you can get this integration points. Here, just trying to quickly show you that the polynomial finite element method, when applied to a standard benchmark problem, and if you look at the convergence in the energy norm, it yields optimal convergence rate. So that's the key takeaway I want to show in this slide. I don't want to go into the details of what the problem is. Typically, if you solve a linear elastic problem with a linear element, the typical order of convergence in energy norm is 1, and you can see that it is close to 1 in all the cases. So this is another example where the power of polynomial elements can be quickly seen. So let's say that we consider a square domain with different circles of different radius, right? And let's say we want to look at the stress distribution in this domain. The small dot here you see is actually a circle, except that you're not able to see the white space within it. Now, if I use finite element method, I would have to generate a conforming mesh. Not only that, the size of the element would be dictated by the smallest feature in your domain. So in this case, the smallest feature is the small dot. And now if I invoke ANSYS, we end up with, at least when we tried, we end up with roughly around 13,650 nodes. Of course, somebody who is a pro ANSYS user may jump and say, I can be smart and I can, reduce this by dividing this into smaller regions and then use appropriate elements. I'm not arguing in those aspects. I'm just saying, if I just blindly say mesh this region with element size of this is what we end up getting. We end up getting roughly around 13,650 nodes. Now, what we do is we can solve the same problem by using what is called as a quadtree decomposition. So quadtree decomposition is typically a data structure that is used in computer science community, where you have a cell which is a square, and every time you divide the cell into 4 subcells. So you divide them into 4 quads, right? And this allows us to quickly go from resolve the necessary features of the problem without having to worry about the regions where the solution might not be changing very much. Right, so as you can see that this problem can be captured through such a decomposition. So now if I look at the number of nodes here, so if I do a pre-mesh in ANSYS, I get 13,000. And with this quadratic decomposition, I end up getting roughly around 6,000, which is roughly half the nodes. So half the nodes, half the number of equations, which implies it takes hopefully half the time to solve the same problem. So now if I look at the solution-wise, so what I'm trying to plot here is the displacement at point A as I refine the mesh. The blue line is from this quadratic decomposition, and the red line is from ANSYS, which uses this arbitrary mesh. Right. So you may wonder. I forgot to mention that there are elements which are like this, which have some additional nodes. Remember, we talked about these elements as transition elements, and then we treat that as a polygonal element. So we invoke polygonal elements wherever that is required. If it is a completely four-sided element, we just treat it as a regular finite element method. But whereas if it has additional nodes, we treat it within the framework of polygonal finite element. So that's where the polygonal finite element comes. So you can see that polygonal finite element method is already converged. The results do not vary much as suppose when you compare with finite element method. So that's a huge saving in computational time. So now if you look at the displacement contour, it looks roughly the same, the left and the right from ANSYS and the quadratic decomposition. So like I said, the harmonic coordinates can also be done in 3 dimensions, except that now you have to solve this on each of the faces. Though again, like I said, it could be computational intensive, but you can have it for certain number of elements and store it in a library, and then we can use it as a traditional finite element method, which can drastically improve the efficiency of your computer program. Again, any domain can be divided into polyhedras. What I'm trying to show here is the convergence of the relative error in displacement as a function of mesh size. You can see that the hexahedral element is shown with a red line, where a polyhedral element is 2.1. Of course, for this simple domain, hexahedral elements are the best suited, and they give you close to convergence of 2, which is as expected. And polyhedral elements are not being bad, they also converge at the rate of 2, which gives us an indication that any domain can be now discretized using polyhedral elements without losing accuracy. Of course, I'm not talking about the computational time here, which would require additional time to do it. I hope that sort of gave you an overview of how things work with polygonal elements. I think I have about another 20 minutes or so, right, Gaurav?
Yes, Dr. Please continue.
Okay. So unfortunately, looking at the pace I'm going, and I don't think I'll be able to finish all the things that I want to cover. But maybe if Gaurav agrees, we can have another discussion maybe later. Yeah. So I think I'll just go with partition affinity method and then stop and then take questions before we move on to the next one. So with partition affinity method, the idea. Sorry.
Yeah, yes, you can please continue.
Yeah. Okay. So the idea is here we detach geometry under analysis. Some of you might have heard this from your lecturer, from your professor Gaurav. So typically, again, it comes to the same question. If I have internal discontinuity or a geometry, finite element method would require that I generate a conforming mesh, and generating conforming mesh for arbitrary regions is quite cumbersome, right? And it becomes even more difficult if these changes shapes or evolves in time, right? For example, think of the case where you have multiple cracks or multiple holes or voids or inclusions. It becomes really a nightmare for stress analysis to generate a conforming mesh. So in terms of linear relative fracture mechanics, we know that if there is a crack, and if you're trying to use linear relative fracture mechanics concept, we know that there is a singularity at the crack tip. And conventional finite element method with polynomials cannot capture the singularity. So one way to do it is to use higher order elements, in particular what is called as a quarter point element, where we move the mid-side node close to the crack tip so that because of the mapping, you will end up with a singularity that can be captured. But this is difficult if this crack is start to evolve, start to merge or branch out. Meshing becomes a nightmare. So comes to the rescue is what is called an enrichment technique. There are different situations where enrichment techniques are useful. For example, if you have discontinuities like in crack, if you have large gradients like re-entrant corners or shock waves, singularities, boundary layers between fluid-fluid or fluid-solid, or highly oscillatory behave as in vibrations or impact. The basic idea is to expand or extend the known polynomial function space with additional function, which necessarily captures the necessary physics of the problem, right? And typically, when you use finite elements to solve, I'm giving an example from a crack. If you use polynomial to solve a particular crack problem, the optimal rate of convergence is 2, but if you apply it to a crack problem, the rate of convergence decreases by half. It becomes 1. So now the question is it possible to retrieve back the optimal rate of convergence with these techniques, right? So extend or extended finite element method is one approach by which you can treat these discontinuities within the domain independent of the mesh. So the basic idea here is to take the conventional finite element approximation, add to it some functions which carry the necessary information of the problem. We'll see for one particular case what this function should look like. But given this as an approximation, we can put this into our Galerkin framework. What you will end up with is an extended stiffness matrix for you to solve, right? These additional unknowns comes from the fact that we add additional functions to your standard finite element base. So what does this additional function do to your approximation? So let's say you have a mesh of quadrilaters, right? And if I concentrate on a particular node, which is shown as a black dot here, the approximation found it takes is represented by this hat. Each of these are the shape functions that correspond from a particular element, and at that point you will see that it becomes 1 and it forms a hat. So this is only a polynomial. But now if I take this polynomial and to it multiply another polynomial which is of higher order, by doing it, what I do is I enrich the approximation within that by this complex shape. So this allows us to custom tailor the function space, which can then allow us to represent the complex physics. So in terms of crack, we know that crack has two distinctive features. One is that at the crack tip, there is a singularity. And behind the crack tip, there is a jump in the displacement field. So with these two information, what I do is I take the standard approximation. I add two parts to it. One is the discontinuous part, which is for regions behind the crack, and a set of functions which is for ahead of the crack to capture the singularity, right? Once I use this, put it into my Galerkin weak form, I end up with system modification to solve. I will be able to capture the singularity even on a very coarse mesh, which is not otherwise possible with finite element method. So now coming back to the same picture, that the one on the top is what you have seen earlier with conventional finite element method. What you see at the bottom is what we can get with extended finite element method. So you can see that the same problem, the mesh does not get updated, but you're still able to capture the necessary physics without much difficulty, just by changing the approximation space. Right. So one thing that you would have to trust me is that I have not used any Photoshop to do it, but these are from the real simulations that we have carried out. Right. So one might wonder, all these are fine for one crack. So here is a situation where there are hundreds of cracks. So this is a part of a bigger domain where you have all these white dashes that you see are the cracks. and this is load and intention. So what happens is that some cracks start to grow, they start to merge, and then after a while it stops. You'll see that all these are captured with X1 quite nicely. I'll just leave it a minute for the movie to get over. So you saw that the crack actually stopped growing after a while, and then the right part of the crack started growing. It started to merge with other cracks as it propagates. So that is a merging again. It changes path. Then for momentarily this part of it stops and this side grows. Again, all this comes from the local energy criteria that is available for the system to dissipate. Yeah. So very complex crack pattern can be captured uh, with much less computational effort. Right? So this is a classic problem where you have a 3-hole in a 3-point bending problem. Depending on the location of the crack tip from the center line, the crack would go to the first hole or to the second hole. So that's from the experiment. And again, I'll leave it for a minute. You'll see that we're able to capture the crack path quite accurately. So it misses. So this is one of the cases where it misses the first hole and goes into the second hole. And all these are done without updating the mesh. We are only updating the region where the enrichment has to be done. And of course, this can also be done in 3 dimensions. So this is crack growth in a typical gear profile. Just to tell you that it also works quite nicely in 3 dimensions as well. There are certain difficulties in implementing XFEM. For example, you need to know where the interface is. You need to know what are the regions where I have to add these enrichment functions. What sort of enrichment function should I use? In this case, we saw that we have 2 enrichment functions. One is the heaviside function for the jump, and some functions which to capture singularity. But if the physics of the problem changes, these enrichment function also changes. So we need to know these enrichment functions, and many times these functions are not simple polynomials, which makes the numerical integration over these elements quite a complex task. So we should come up with efficient ways by which you can integrate over the regions that are intersected by the discontinuity. These are from the implementation perspective. The other perspective is that first of all, you saw that we add additional terms, which implies we also have additional unknowns. So this could lead us to a larger system to solve as opposed to what we will have in a finite element setting. And then the condition number is drastically affected because of the choice of these non-polynomial enrichment functions, which are very localized. So there has to be ways by which you can improve the conditioning number. The other difficulty with XFEM is that, of course, some of these difficulties are already addressed. It's known now, but here I just highlighted it to show that these things have to be kept in mind when somebody is trying to implement XFEM or use XFEM. The region of enrichment is very localized. So this introduces 3 regions. One is the part where you have completely enriched, the part where you have not enriched, and the region that connects these 2, which is called as a blending. And in blending regions, we lose approximation property. We get some erroneous results. So care has to be taken in treating these blending regions efficiently. And as I pointed out earlier, the functions that we are trying to integrate can be singular, not just non-polynomial, but cannot be singular. So care must be taken to integrate these functions accurately so that the results that we get make some sense. Yeah, with that, I think XFEM part is done. So Gaurav, shall I continue for another some time?
Yes, Dr. Sundar.
Because it's already
We'd love to hear more on this. I think we are getting to know some wonderful things from you, and I think all the participants would agree that you can continue and you can take your time.
I think I need at least another half an hour to. Sorry, I made it a slightly longer one.
I think it is fine. It is fine with me, and the participants also I think would like to know more. So I think you can continue, Dr. Sundar.
Okay, all right. So thanks for the patience. So the next one is on isogeometric analysis. this is contradictory to what we just saw. In the one that we saw extended finite element method, we want to decouple the geometry analysis. So we want to have the analysis independent of the geometry. But here we want to combine them together. We want to have a seamless coupling with the geometry. So remember this figure that I showed you or flashed you at the earlier presentation, where it shows a typical design cycle. We have a CAD model, then we have the analysis suitable step called the meshing, then the analysis, right? So with isogeometric analysis, the idea is we can go from CAD to analysis directly without this complex time-consuming discretization step. And this is called isogeometric analysis, right? And this gives a seamless integration with the CAD model. The good thing is it can represent the geometry exactly. So if I now want to represent an arc or a quadrant of a circle or a circle, if I use finite elements, I may not be able to represent it, but with the NURBS or isogeometric analysis, I can represent it exactly. And we can also generate higher order elements, which is not that trivial with finite elements. We can have higher order continuous elements quite easily. And apart from just H and C refinement that we have seen in finite elements earlier in our coursework, we also can have K refinement, which is a combination of H and K, where you can refine it and then improve the order of continuity, or you increase order of continuity and then refine it. So that sort of a flexibility this provides. So if you want to look at the philosophy, why is it called isogeometric analysis? I think we should go back to a friend finite element method, which is called as isoparametric formulation. So if you look at why it is called isoparametric formulation, is because remember we write the shape function in a parametric space. We denote it by psi and eta, the Greek letters. That is in the parametric space. We call that to be parametric space. And we use those functions to represent the unknown field. So that's the first step that we do. We say, okay, U is written as linear combination of these functions, and these functions are in the parametric space. And now we use the same function to represent the geometry. So that's why it's called isoparametric. Iso means same as the parametric space. Whereas here what we do is we do a contradict. We do it slightly different. So we have functions that are representing the geometry, and we use the same function to represent the unknown field. So isogeometry, same as geometry. That's something that you can keep in mind. In finite elements, the approximating functions are polynomials, whereas in isogeometric analysis, especially if you are using non-uniform rational B-spline, they are not simple polynomials. They are rational polynomials. So rational polynomials are polynomials which have a numerator and a denominator, where both of them are polynomials. Of course, it also has its own share of disadvantages. Some of them are that the NURBS do not have Kronecker delta property, which makes application of boundary conditions quite tricky. And CAD model only provides the boundary information, whereas finite element method would require a volume information, so which implies you would have to do a small step, again, which can be done on the fly, have to be done to do it. The reason why I pointed out this particular point is that remember we talked about a basket which said boundary representation, right? So isogeometric analysis is a good candidate for boundary element method, where the CAD model gives the boundary information, and the boundary element method requires only the boundary information. So which implies, that gives a very good approximation for your problem. And like I said, NURBS are rational polynomials. So the numerical integration scheme that we have works good for polynomials, not for rational polynomials, which implies numerical integration is now going to be a tricky task. So CAD has to be taken to integrate these polynomials efficiently. So non-uniform rational B-splines are basically written from B-splines, which are Bezier splines. They are polynomials over polynomials. They are written by what is called as a knot vector, which is a non-decreasing set of coordinates in the parametric space, right? So and this parametric space can be anything. So it could be in the physical space also, although it is called as parametric space. The nice thing about this is that if I want to represent a quadrant of an arc, let's say, with NURBS, all I need is just 3 points, and I will be able to represent this arc exactly. And having represented that using those functions, I can use the same functions to solve the problem. So which implies now my geometrical error is sort of eliminated from my analysis, right? So whatever is there in the CAD model is what I have in the analysis, which is not the case with conventional finite element. There is always a geometric discretization error that goes into it. And of course, non-information B-spline also has the nice properties as finite element method. They satisfy partition of unity. They are non-negative. They, like I said, we can generate higher order continuous functions quite easily, and they can be used within finite element framework. So this is not possible if you have conventional finite element approach. For example, this is a typical case plate with a hole there for which there is an analytical solution given by this. If I were to use finite element method, I would have to discretize the entire domain, but with isogeometric analysis, all I need is these blue dots, which exactly represents the geometry. Of course, if the geometry is a straight line, the blue dot lies on the geometry. If it is a curve, the dot lies outside the geometry to be able to represent it. Yeah. So now, if I look at the error, let's say in displacement as a function of degrees of freedom, what I have plotted here is for different order of shape functions. Lagrange polynomials with quadratic is shown in this color with a plus sign, right? We have NURBS p equal to 1, which is a linear function. Please note that NURBS p equal to 1 and Lagrange p equal to 1 are identical, so that's the reason why I have not shown it here. Of course, between p equal to 1 and p equal to 2, you see a drastic difference, and as you increase the order of the polynomial, the approximation increases, so the error actually decreases. So then, in fact, if you see NURBS p equal to 2, it is already better than Lagrange p equal to 2, which is a good sign. And p equal to 4, the error is already at 1e minus 7. So even for the same degrees of freedom, so you can see that this gives a very efficient method, not only in terms of representing the geometry, but also in terms of capturing the displacement error. One application what people try to do it is you use optimization directly from CAD model. So the geometry is represented by IGA or NURBS, and then we use boundary element method or the scale boundary finite element method to solve this optimization problem. So you can actually go from defining the hammer from this shape to this shape, which could be depending on certain certain constraints. It could be the weight or the volume, or it could be some other stress constraint. All this can be done without generating an intermediate step of meshing the domain. So you go from the CAD model directly analysis quite easy. That's a major advantage of it. I think that's all I have for isogeometric analysis. Right. So the next method I want to talk about quickly is what is called the scale boundary finite element method. Here, I call it as the best of the two worlds, the finite element method and the boundary element method, right? So this was actually introduced for dynamic foil structure interaction problems for unbounded problems by Song and Wolf in 1997. But ever since, it has been applied to other fields such as fracture mechanics, fluid mechanics, you name it, it's now being applied to various problems. The beauty of the method is that it is semi-analytical. And the reason why I say it is finite element, it is the best of both, is that like finite element method, it doesn't require any fundamental solution. And like boundary element method, only the boundary is discretized, right? So it's quite a recently introduced method. It's only introduced in 1997. So it's not as old as finite element method, but it has a lot of advantages when compared to finite element method. So I'm not going to go into the detailed math behind it. I'll just give you an idea of what it does. The basic idea in scale boundary method is you introduce a coordinate system we call it as a scale boundary coordinate system, which basically is a scaling system. So you go from X and Y to a system which goes radially from the point O to the boundary, and another coordinate that goes on the boundary, right? So we call the point O to be the scaling center, and the condition is that from the scaling center, the entire domain should be visible. In the sense, if I scale the point in all the directions, I should be able to construct the boundary of this domain, right? So that's why it's called scale boundary method. So once you have the representation of the boundary in terms of the new coordinates, we also use this the same approximation for the displacement. Once you have the displacement, we write the strain using the displacement. So we follow the same Galerkin procedure to do it. But now, instead of working with a Cartesian X and Y, we will work with a new coordinate system called the scale boundary coordinate system in terms of xi and eta. So xi goes from 0 from inside the domain to 1 outside on the boundary, and eta goes around the boundary, right? So the discretization is now done only on the boundary, and within the domain you get analytical solution. That's the reason why it is called as a semi-analytical method. So this leads to an eigenvalue problem, which again is not too difficult to solve. Again, if you want more details of it, you can talk to me later, because the derivation of this is quite lengthy. But what I'm trying to tell you here is that it has some nice advantages if you want to solve, let's say, fracture mechanics problem, because remember, polynomials cannot capture the singularity, so people introduced XFEM, but XFEM requires the so-called additional enrichment functions. All these are not required if you use scale boundary finite element method, because the solution within the domain is analytical, so I can capture the singularity quite efficiently, in fact, accurately with scale boundary finite element method. Right, so I'm not going into the details of this. I just want to come to the same problem just to show how good the scale boundary is. Right, so this standard benchmark problem, the thick cantilever beam problem, for which we have analytical solution. What I'm plotting here is the degrees of freedom as a function of displacement. So here I've compared different methods. We have already seen polynomial finite element method. We have not seen smooth finite element method, which comes at the next part. So the green line is a scale boundary finite element method. You can see that it's already doing much better when compared to any of these approaches. And this one is, I think, yeah, scale boundary with polynomial order 2, and this is with polynomial order 1. They have very good approximation properties. All these are quite useful. So coming to the crack problem, if let's say you have a plate with an inclined crack, the solid line represents a crack with an angle. If I were to use finite elements to do it, this is a mesh that I would have to have, extremely refined mesh close to a crack tip, so that I can capture the necessary physics of the problem, right? Whereas with scale boundary finite method, this is the entire mesh that I would have to have, because the solution within this domain is analytical, so I can capture the singularity exactly. So now if I compute the stress intensity factor, when we compare with the solution that is available from the literature, the stress intensity factors are quite close, both K1 and K2. And this on a typical Intel P8600 machine, it takes less than a second to give you the stress intensity factor, which personally I think is very fast when compared to finite element method, because with finite element method you need to have an extremely refined mesh. Have an extremely refined mesh, which increases the computational effort. So very, very efficient method, but the shortcoming of that is that it's still at an early stage. Applying it to a three-dimensional problem is still a work in progress. It can also be applied to polygon elements, because it doesn't differentiate quadrilateral region or a polygonal region. Any region can be applied as any region can be treated as a scale boundary region. And here what you see is a crack growth problem. There is a local remeshing that is done, which is counterintuitive, counter to what I just said about extreme. But if you look at the overall degrees of freedom, this is much efficient than extreme, I would say, right? So what we also did was to combine scale boundary and extreme together. The reason is scale boundary does not require the knowledge of enrichment function, but there is a local remeshing that is required. On contrary, extreme does not require local remeshing, but requires the knowledge of enrichment function. So we thought, would it not be best if we combine both of them? So, we don't need to know the enrichment functions a priori on one side, and we don't need to remesh locally as the crack evolves. So this is what we will have in a conventional extreme setting, where we have the crack represented by a solid black line. Then you have regions which are to be enriched, with functions that can capture the singularity at these two regions and the jump at these places. So what we proposed to do was to replace a certain region with scale boundary. So within this region, the solution is analytical, semi-analytical, whereas the rest is finite elements, and this region is extended finite element. So the beauty is now, like I said, we don't need to know enrichment functions a priori, and we don't need to remesh locally as what we would require in scale boundary finite element method. So again, this is the details of how we can couple the extreme with scale boundary finite element method. Again, a simple transformation is all we need to combine both of them, because on the boundary when we use scale boundary, on the boundary we use finite element method. So the shape functions are already compatible, so we can actually with a simple transformation we can sort of combine these two techniques together. And remember, one of the problems that we had with extreme was the conditioning number. The condition number is really bad when you increase the number of degrees of freedom with extreme, which is what I've shown here for a problem with an edge crack. So what I plotted here is the scale condition number as a function of degrees of freedom. What you see is with extreme, it actually grows at the order of 2, whereas with scale boundary finite element method, it's really small and it's comparable. You can still treat it with nonlinear iterative solvers quite efficiently as compared to extreme. So that's the major advantage we do it. With this, we can also now do a 3-dimensional problem, as opposed to just having scale boundary as one method. I think that's all I have for the scale boundary finite element method. I think this is the last one in my talk, which is smooth finite element method. Here, this takes a different thought process, right? So here the idea is improving element performance. So it is built on the fact that we have sophisticated meshing algorithms. We have sophisticated finite element codes which can be parallelized, highly parallelized, right? For example, we have good meshing algorithms like Gmesh, which is an open source software, which can give you 1 trillion tetrahedral elements on a very complicated shape in just less than a minute, right? So, but we know that tetrahedral elements are really bad because they are overly stiff. They cannot capture the bending accurately. So we need to have more number of elements, which increases the computation power. So of course we can now use the polygonal finite element method, but then you need to change your meshing algorithm, and also most of the finite element code has to be modified for you to be able to use the polygonal finite element method or any other technique. So the idea was, can we use existing elements but then improve the performance of them? For example, it was mostly focused on using triangles or tetrahedrals as a base element and improve the performance of the element, right? So the basic idea is to, over each element or a region, we write what is called as a smooth strain field, which is nothing but a weighted average of the compatible conventional finite element strain field, right? So when I say weighted average, you take the finite element strength field multiplied with the weighting function. And the beauty of this is that this is a continuous function within an element, and this is a weighting function which is also continuous. That's what we assume. Now, when you write a weighting average, you introduce an integral. Because both of them are continuous functions, we can apply Gauss divergence theorem to it. So this boundary integral can now be transformed to a line integral on the boundary. So interestingly, what happens is that if the weighting function is a constant function, and when we use the Gauss divergence theorem, the derivative that is there on the strain field gets transformed to the weighting function. That becomes the domain integral. The line integral on the boundary will just have the displacement multiplied by the normal, right? So if the weighting function is a constant, the domain integral vanishes. So essentially what happens is that the domain integral is now transformed to a boundary integral. Not only that, you don't need the derivative of the shape function. That's a major plus point, right? Interestingly, what happens is that that integral can be quite efficiently calculated just by knowing the property of the shape functions on the boundary, right? So the shape functions on the, for example, if you are using a linear element, the shape functions on the boundary are linear, and integrating a linear function, you just need one integration point at the center, so which implies you don't need to know the derivative of the shape function. Not only that, you also don't need to know the functional form of your shape function. All you need to know is what is the value at the center of the edge of an element, so which is basically 0.5 in this if you are using a linear element. So this is a major advantage when compared to other techniques, because you eliminate numerical integration error. You don't need the derivative of the shape function, which implies you can work in the physical space. Since you work in a physical space, there is no mapping involved, which implies you can now you can also have concave elements. Remember, one of the setbacks that we had with finite element was that the elements have to be good shape. So now all these are eliminated. We can work with concave elements. We don't need derivative shape functions. There is no mapping, and most importantly, there is no numerical integration. So many errors are actually reduced when we use the smooth finite element method. So now the question is, how do I choose a smoothing region, right? So there are different ways by which you can smooth the strain field. One popular way is called as a cell-based smoothing, where you take the conventional finite element method, conventional finite element, and use that itself as a smoothing region. The other popular approach is node-based smoothing, where you take the compact support of the node and then use that as a smoothing region to write that smooth strain field. The other approach is what is called the edge or edge-based smoothing in 2 dimensions and face-based smoothing in 3 dimensions, where you take the compact support of the edge and then use that as a smoothing region. For example, the compact support of this node could be this shaded region. So this shaded region is where you write the smooth strain field. Whereas for an edge-based smooth finite element method, you would use this shaded region, which is basically compact support of this edge, as the region for writing the smooth strain field. So by doing this, there are a lot of advantages, not only in terms of reducing the effort, but in terms of the property of the shape, property of the stiffness matrix that you get. So nice features, again, to summarize, it is insensitive to mesh distortion. There is no isopermanent mapping involved. You don't need derivative shape function. Importantly, it is insensitive to locking. And of course, it is rank deficient when you use one subcell, which is same as when you use one integration point in terms of 4-noded element. It's best suited for triangular elements. And when you combine it with enrichment techniques, it avoids the integration of split singularities. And of course, when in XFEM, it reduces the complexity of subdivision and so on. Right? So these are some nice features of smooth finite element method. Again, the same problem. Of course, plotted differently. Now here we are showing the energy norm as a function of space, and different approaches are shown here. Let me just quickly summarize. So the one on the top is the conventional finite element method with triangular elements. One below in green is finite element method with four-noded quadrilateral element. Red is edge-based smoothing. Blue star is node-based smoothing. And this pink circle is equilibrium finite element method, which is again based on cell based. So you can see that when compared to finite element method, either T3 or Q4, the smooth finite element method gives you, for the same degrees of freedom, more accurate solution. And as you at the same time, the approximation properties have not changed, so you still need optimal order of convergence as you refine the mesh. So this is a boon, because if I want to stick to using triangular elements to to discretize my domain, instead of using a finite element approach, if I use let's say edge-based smoothing, I can see that I can, for the same degrees of freedom, I'll have a better result when compared to finite element method. Right. So the last one that I want to quickly touch upon is, all these are fine. I mean, all these we develop our own code, but commercial software are being used by industry. So there should be a way to port this into commercial software like Abacus or ANSYS, right? Otherwise, first of all, one thing, we cannot solve complex problems. We are, unless we have a very sophisticated code, a highly parallelized code, which we can do it, or we leverage the power of Abacus and solve this problem. So one way to do it is, Abacus has this nice feature called user element interface. With user element, what you can do is you can define your own element. You can, within that, you can define your own stiffness matrix, shape function, everything. And Abacus understands it and solves it for you. So what we have done successful is that we were able to implement almost all of them except for isogeometric analysis. We have implemented scale boundaries, smooth finite element method, polygonal finite element method, even XM within Abacus. Of course, XM now is in Abacus now as a part of the module, but the rest are not there yet. But it is possible to cheat Abacus in solving problems using different methods. The way we do it is, we generate the mesh. For example, if it is a polygonal element, we generate the mesh outside Abacus, and we do a simple pre-processing. We use MATLAB, but anything can be used. Python can be used, or any other software can be used, which basically generates an input file that Abacus can understand. So it will have terminologies that Abacus can understand, so which you'll see in the next slide. And then we write what is called as Abacus user element, where we define and write our own stiffness matrix, shape functions, everything. And then there is a way in which we can tell Abacus to use our user element and not use built-in functions. So again, I'll show you what it is. And then once you have the results, Abacus cannot post-process the results because these are not the standard element type. What we do is we again take the results from Abacus, either visualize it as using open source softwares like ParaView or some other software. But the key thing is, now we are able to use the power of Abacus solvers, be it nonlinear, linear, and we don't have to worry about writing the full finite element code. All we have to do is develop the user element for it, and then Abacus takes care of the rest of the assembly and so on. That's a major advantage in my opinion. Okay, so now if I were to, I'm just going to give you a quick understanding of how it would work. So Abacus input file has certain keywords. So you can define the elements, you can define its material property and boundary conditions, so on and so forth, right? So typically I would want, let's say I want to solve this problem, a square domain with these three elements. You can see that elements 2 and 3 are standard elements with 4 nodes, 4 sides, whereas the first element is a polygonal element. It has 5 sides basically. So all you have to do is we have to separate them out and then define a new user element for each of those categories. give the element connectivity and the property. For the rest, you can use Abacus's built-in functions to do it. So this is what necessarily goes into the input file. So this is what you will generate in the input file. In the user element, there is a standard way by which you can do it. You cannot change the first part of the user element, which is what Abacus can understand. But what you can do is be able to write within the subroutine. So again, Abacus user element subroutine is in Fortran. So this is the function call for the user element. For linear elasticity problem, quasi-static problem, the only thing that you would have to worry about is RHS, which is basically the right-hand side vector, and A matrix, which is basically a stiffness matrix, right? So now inside this user element, we will write the same way as we would do in our own code when computing the elemental stiffness matrix. So you'll have a Gauss integration loop. You'll find the necessary matrices and then find the stiffness matrix locally. And that is what will go into this part of it. So that gives you the user element for a particular method, right? So, and then to execute, since we are using our own user element, the only way to do it is to invoke Abacus from command line. And the way we do it is Abacus, we give the Abacus input file, and we say Abacus to use the user element, which is a Fortran file that we have generated. So this will force Abacus to use the input file that we have generated along with the Fortran file that we have given it to Abacus. Then, like I said, we can then use Abacus power to solve the system of equation. Assembly is taken care all by itself. It is highly parallelized, which implies that degrees of freedom you don't have to worry about it. Of course, for more details, you can go to my GitHub page where we have posted some of the code which are in Abacus. You can do it, or you can write to me. I'll find time to respond to your email and questions when it comes to implementation app. All right, so that comes to the summary of my talk. So hopefully I gave you a basic idea of different techniques: polynomial finite element method, extended finite element method, isogeometric analysis, scale boundary, and smooth finite element method. Of course, very, very basic standard benchmark problems. The performance of these methods were discussed, and application to linear diffraction mechanics were presented. Right. For more details, you can refer to the literature or some of my papers, where the details of the method and its robustness are discussed in great detail. So thank you for listening to me. I'm sorry I've taken half an hour more than what I was given. Yeah, thank you. I'm happy to take any questions that you may have.
Thank you, Dr. Sundar. It was a wonderful presentation. I would say that this is one of the best presentations I have personally listened to in a long time. And I also hope the participants also have gotten to know about so many different things which they usually don't learn in the regular courses. And so I also like to thank you for taking out time from your busy schedule to inspire the participants and our students. We have our faculty members here from our department. I would request them, if they would like to ask any question to the speaker, they can please unmute and ask.
Thank you, Gaurav, for summarizing that.
Yeah, Gaurav, can I ask some questions?
Sure, Dr. Sundar. Dr. Shyam Sundar, you can please.
Professor Sundararajan, my name is Shyam Sundar. I'm assistant professor in this department here in mechanical engineering. My question is like, you must be using some open source codes also, like, some of the open source code like Phoenix or maybe Calculix, etc. And you are using Abacus also. So can you give some sort of an overview in terms of their capabilities, their performance, something on this?
Yes. So yeah, like you rightly said, we do use Phoenix. We have not used Calculus, but the syntax of it is very much like Abacus. We have used also FireDrake, which also looks like Phoenix.
Okay.
Phoenix is good, powerful in my opinion, but the disadvantage is that For now, it is restricted to only triangular elements, and we don't get to get the core of the code. You will not be able to modify the code that easily. If you're trying to develop a new element, for example, that may not be quite straightforward from the Phoenix implementation perspective, unless you get to the core of it, modify the C++ code. That's where it is written in. But if you're trying to look at solving a problem quite efficiently, I think Phoenix offers a way to do it. Of course, with limited capability. For example, it cannot do contact problems yet. Those are some bottlenecks. Because the way it works is that it works directly with the weak point. So unless we pose a contact problem, which typically is solved either as a variation problem or an optimization problem, Phoenix cannot do it at this stage, at least. So there are some shortcomings with it. So, but otherwise, if there are no contacts, it can handle multi-physics, multi-fit problems quite efficiently. It is highly parallelized. But the downside I now see it is there is no documentation that is maintained with, as with any other open source software. Earlier, it used to be very good. There used to be very good documentation, but I think now they are porting different things. They moved from a conventional implementation to Docker facilities. I think that's the reason why documentation is taking a backseat. But I think it eventually. But the community is very vibrant. If you write to them, provided the question is not too trivial, they are there to help you out. But if the question is too trivial, they don't answer. But if it is something that they can, they are very vibrant, and they are very helpful.
And my second question, sir, is like we are working on non-isothermal viscoelastic flows. So do you know any open source code based on FEM which can handle such flows? Non-isothermal viscoelastic flow, basically polymer melt spinning, etc., something like that.
Unfortunately, no. We are also working on it. I don't know if you know Professor Krishna Kannan and Parag Ravindran here, IIT Madras. We also work on viscoelastic flows. So we develop our own programs for that. So we have not come across any. So sometimes we implement it in Abacus. We have a license for Abacus, so we implement it in Abacus, whatever we try to do it. But many times we write our own codes for that. I have not come across any open source that can do it yet.
Okay, thank you, sir. That's all from my side. It was a really good talk, sir. Thank you.
Thank you very much.
Now I request Dr. Anish. Dr. Anish, you can ask a query.
Hello, Professor. Thank you very much for the talk. It was really insightful. And I have one specific question on I think one specific method that you mentioned, scale boundary finite element method, which I think you mentioned it is good for fluid structure interaction problems. I am working on something very similar problem. In fact, something like human phonation problem. I was mainly using ANSYS workbench for this problem. But what I came across is that whenever I use this ANSYS workbench, it is giving some sort of negative volumes wherever it come across some kind of large deformations. So my question is now I think added question to what Professor Shyam has asked. So are there any commercial solver available already, or some open source solver already available with this particular specific method?
For scale boundary, no, there is no open source yet.
Okay.
In fact, none of the methods that I've talked about, except for isogeometric analysis, others don't have an open source yet. So it is all custom made. Researchers have their own code, some willing to share. For isogeometric analysis, there is this open source called GeoPDE, which works reasonably well.
Could you please repeat that? GeoPDE.
GeoPDE.
Okay.
That's a MATLAB toolbox that works reasonably well.
Ah.
But I think that is also limited to elasticity and linear convection problems. But if you know how to do it, then that could be quite efficient doing it yourself. But yeah, for the other methods, there are no open source available yet.
Actually, this is a very simple geometry. So, would it be possible if I can write to you in detail about this problem? Because maybe some of the available codes with you may be useful for this.
Yeah, please feel free to write to me. I'll respond through email. No worries.
Thank you very much.
I'll be interested to explore these methods to other problems also.
Sure. Thank you very much. Thank you very much.
We also have Dr. Amit and Dr. Shomajit with us. If you have any questions, you can please ask.
Good afternoon, Dr. Sundar. Thank you very much for excellent talk. Maybe I misunderstood something, but you can maybe just correct me if I'm saying something wrong. So the SBFEM method, you said it is semi-analytic, and so does that? And you said that within the domain or the element that we found, the solution is analytic.
Yep.
So it is applicable to the problems for which we know the analytic solution within the domain. Is that right?
No. So again, so the process of converting. So I skipped some details here. Are you able to see my screen?
Yes, I can.
Where I've come to the point where we talked about boundary distance. So we introduced this new coordinate system, right? The scale boundary coordinate system, which converts x and y to zeta and eta.
Okay.
And if you do the math, you end up with the equation that is shown here, which we call as a scale boundary equation.
Mm-hmm.
The beauty of this equation is that this is an Euler-Cauchy differential equation.
Okay.
And for Euler-Cauchy differential equation, we can write a generalized solution in terms of polynomial, which is analytical, right?
Oh,
and that's why.
Okay.
So this can be applied for any problem, right? So any operator, any differential operator will lead you to, this form of Euler-Cauchy differential equation, and for which we have an analytical solution.
Okay.
So that's the reason why it is called. That's why it's called semi-analytical.
Okay. Thank you.
Thank you.
And so when you say on the previous slide that the entire boundary should be visible from the scaling center, so that means we don't want overhangs basically. Is that right?
What do you mean overhangs?
For example,
concave.
concave, shapes like an algae or a amoeba or something, where
Yes,
if I draw a straight line from the scaling center, it may cut the boundary in more than one place.
Exactly. Yes. So
okay.
we cannot afford to have that. So in those cases, what we do is we divide the region into smaller regions, and that's what you saw in this example, where the domain itself is divided into polygons.
I see.
And we can use scale boundary on each of these polygons. Although here, of course, if I consider the crack, then the domain becomes concave. So one way to do it would be to divide it into smaller regions. So is the case with this example. So in this example, if I create the crack tip here, sorry, scaling center here, this becomes a concave region. So I will not be able to see this part of the domain. That's the reason why I have divided into two regions, where from each of the scaling center, I will be able to see the entire domain, which will then allow me to solve the problem.
Okay, another question. Again, I might be making a mistake in understanding this. So the XFEM, we said that we need some enrichment methods. So the enrichment methods have some broad requirements. Like what I am concerned about is like is it that I have to choose my enrichment functions very carefully, and there is a small class of functions which I could choose, in the sense that am I influencing the solution which I'm going to get by choosing my functions very carefully, or is the class of functions which can be used relatively broad, where I can say that my solution is independent of the choice of my function?
No, solution highly depends on the choice of the function, right? For example, in this case, if I choose to ignore this function, the red one, there is no way I can capture the singularity, and my stress intensity factor will not be accurate. So the choice of the function, the knowledge of the functions is very important here. So that sort of put a constraint on, if I have a complex physics, I would not know what these enrichment functions are. For
Yes,
example,
exactly.
For example, if I have a crack at the bimetal interface, the enrichment functions are really complex. Okay, we don't know what those enrichment functions are, and of course, there are ways by which we can derive the functions, but after you derive, you see that it's very complex. Same is the case if I have a crack in an orthotropic material. There, since the material is orientation dependent, the functions also becomes complex. Now, if I choose some other integration function, which let's say is for an isotropic material, but use orthotropic constitutive law, you'll capture the singularity, but the strength of the singularity will not be the same, and the result that you get in terms of stress intensity factor or the stress distribution will not be accurate.
Okay, so basically, yeah, please go ahead.
So you need to choose appropriate enrichment functions to capture the appropriate physics.
Okay, and so one has to be quite vigilant to be able to understand that the solution, there is something wrong in the solution, because if it is very closely tied up with the choice of the function, then there may be some subtle flaws which may not be immediately visible if the person is not vigilant using XFEM.
Yes, very true, very true. You're rightly said.
Okay, thank you very much.
Yeah, thank
you. Dr. Somajit, do you have any question to the speaker? Okay, so the participants, the student participants have not written anything in particular. So on the students' behalf, excuse me, on the behalf of the students, I would like to ask two questions to you, so that the students also benefit from your opinion on the same. I would like to ask on behalf of the students that what are the current and future research directions in computational mechanics? What should they choose to work on if they want to pursue MS or a PhD in the field of computational mechanics?
Okay, that's a very tricky question to answer. But anyway, I'll give you my my opinion on it. So I think now the future trend would be just not to develop methods because of the sake of it, which was the case at least a few years back. Now we need to also have certain physics that we want to address it. And the way we would want to look at is that we have now a zoo of Galerkin's methods. So we want to, and not one method can solve all the problems. So we need to be able to use some of the techniques in combination to be able to solve a particular problem. So that may not be readily available in any commercial software. So we might have to write our own code. So you should have some inclination towards developing code, debugging, and any method that you pick can be applied to other problems also. So it's just that it depends on whom you work with. For example, if you work with a group which only does scale boundary, you will only end up doing scale boundary for your research. Doesn't mean that it solves all the problems. There are a variety of things that have not been explored even in XM, even in smooth finite element methods. So anything, it's important that you also have some physics attached to it, and not just a problem by itself, not just a method by itself, which I think will not be appreciated by the journals at this stage, at least in my opinion. I don't know if
So,
that answers your question.
yeah, so if I summarize it, students should also focus on learning the physics behind the problem, then simply focusing on understanding how to solve a problem.
Yes, yes.
If I put it correctly.
Yeah. I mean,
So
have some
in short,
understanding of the physics. Physics is important because I've not shown you my research vision. The research vision that I have is moving boundary problems, right? So this moving boundary problem can be seen on all fields. You know, it can be seen in, for example, a fluid structure interaction problem. Moving boundary is there in a crack propagation problem, or it could be in a thermal problem where there is a solid and a rocket fuel in the flame and the structure problem. So there is always a moving boundary problem. But the governing equations for that is always a simple Poisson's or a nonlinear Poisson's equation. So you focus on what is the physics, but then that is important, but also learn the way by which you can solve these problems efficiently.
so one more question that I think students would like to know about. If somebody chooses not to go for a research in the area of computational mechanics and instead wants to join an industry, then what do you think are the career opportunities in the field of computational mechanics if one has done well by acquiring skills related to the field of computational mechanics in undergrad or postgrad?
Okay, so I can share based on the experience that I have when I was working with General Electric. So at least in my what I've experienced is that people appreciate not just how to use the software, but also interpret the results that the software gives you. So that's where your role as an engineer comes into picture. So not just getting color control plots, but to understand why this happens, reason out logically based on certain equations, and which will then help you address certain problems. You know, for example, it could be redesigning a certain component based on the stress levels that you see. All these are what is essential. So you should definitely focus on the fundamentals. Also have a good understanding of how a finite element method works. So you know whether the results that a software gives you, make sense. So those are very important. I mean, I can probably share this small story, which I happened to be in one of the review committee for an industry. So they were trying to look at the fundamental frequency of a gearbox, right? So they have done complex meshing, did everything in analysis, and they said the first fundamental frequency is 0, which which immediately should strike the person who did the analysis is that should not be the case, because the casing, the gearbox completely fixed. So the first fundamental frequency should not be 0. There has to be some problem with the analysis. But she said, this is what I get. And remember now, if somebody goes with the design of this and manufacturing it, that would be a fatal accident. So when we probed into it, it so happened that this engineer who did the stress analysis forgot to arrest or couple one of the components with the rest of the components. So this one particular component was freely floating in air, because of which it gave a rigid body motion, which led to a zero energy move, zero eigenvalue. Problem is, he did it in answers. The answers did not say that there is a rigid body move. Just spit out saying this is a rigid body mode. So it wanted the user to know that there is a rigid body mode and go and constrain it. So what I'm trying to say is that it's not just important that you know how to use the software, but you also know what goes into the software and what software spits out in terms of the result. So you should be able to analyze the result, give an engineering judgment to it. That's where your role would be appreciated. So it's important that you have good understanding of everything. You may not work or develop new methods, new elements, that is fine, but you should know how it works in the back.
Thank you. So I hope the students have gotten the answer. So One final question. Sorry for asking too many questions. One final question. It is a general question. Is what steps we should collectively take, all the institutes, to work towards an indigenous commercial modeling and analysis software to cater to the requirements of our industries, the Indian industries. So is it possible to have a software of like Abacus or Ensys, given the amount of work they've already done? Are we positively looking forward to that? Is there any policy, or we should simply like what is your opinion on this?
So that is something very close to my heart. I've been talking to many people, saying, if the computation mechanics people in India should come together. See, there is a misconception. Computation mechanics people are not the people I'm talking about who uses it. I'm saying the people who actually actively develop. They should come together, come up with a process, a procedure by which they can develop a finite element software, which the industries can use it. So many times what happens is that big companies afford to buy these licenses, they run the finite element, get away with the certification also. The small scale industries and the medium and small scale industries are the ones that get hit because they cannot afford to buy these softwares which are very expensive. So they many times do a over design of it, which make them bulky and also expensive. If they had supported it with some analysis, try to reduce it, that would have been advantageous. But the problem is, we don't have a software to cater, like you rightly said, cater the needs of the Indian industry. But for which I think all the people working on computation mechanics should come together collectively and then start developing it. It may not happen overnight. It may not even happen in the next 2 years. But at least if we put consistent effort, in about 5 years or so, I think we can have something tangible, which can be cost friendly for the Indian customer.
In this context, I would like to add, there is Professor Dr. Sundar, you may be aware of Elmer FEM.
Yes, yes.
It was developed by, like in collaboration with the Finnish universities by funding from the government of Finland. I think their Center of Science. So there is another aspect to it is, yes, I appreciate that if we would have something which we can make useful for Indian industries, like something maybe backed by the government or something like that. But what is the harm in like leveraging the, we have many high quality finite element packages, for example deal.2, you may be aware of that one.
Yes, yes.
And even Elmer FEM, like several decades of effort has been put into that, and they have already made a lot of progress, and they are all open source and free to use. So like implementing everything from scratch is a big effort.
Yes.
And then all the testing which has gone into these softwares which have existed for decades, so many bugs have been fixed, and the chances that if we develop something on our own, we may introduce bugs which will some of them may be subtle and may show up only in some special conditions. To iron all of them out will be like a huge task. So won't it be more practical to base off something which is already existent and proven to be working well?
Yeah, very true. Rightly said. But the only counter argument that I have it is that it is not ours. We don't own it. So that is something that as a computation mechanic, when we develop code, you get that sort of excitement when you debug the code and say it works fine for all the test cases. That you will not get if it is a deal 2. I mean, deal 2 is a fantastic software. I'm not denying it. There is a lot of effort that has gone in, which is good. There is also called DiffPack, which is very similar to deal 2. Wonderful libraries are there, just not Indian. That's all.
Okay.
Nothing against. It's just not Indian. That's all I would say.
Okay.
So we have potential to do it if all people in India come together with a single goal in mind, I think that is possible.
Okay.
And with the expertise that we have, we can, the things that you said, we can get something something working really fast, given that we can foresee what problems may occur and how to debug, because we have all these open source softwares which are already tested. We can leverage the learnings from that and work on top of it. For example, how do you structure the entire code can be learned from deal 2 or dispatch. We don't have to brainstorm everything. But, you can write everything from scratch, which could be Indian.
I completely agree with that, and I think ISRO has already taken up that initiative. I'm not sure
Yes,
to what extent.
they have something called fees.
Yes, which is I'm not sure if they're trying to develop software for their own requirements or or for the general public use.
No, I'd say it is for general public use. I mean, the licenses are very cheap. It's called FEAST, FEAST. But they don't give you the full source code.
Okay.
So, which to me is again a bottleneck for me, because then if I want to develop some new technique, I would not be able to modify it there. I will not be able to use their software.
Okay.
So if at all it has to be there, it has to be completely open source, like Deal 2 or something, which can be libraries, and then people can build on top of it, and then can use it.
Okay, so I think if you come across any initiative by our government or any public funded institution, I personally would like to be a part of it, so that I somehow, whatever small manner, can contribute towards development of such a software. So do let us know if in through a meeting of public funded institutions, if you come across such discussion or such plan.
Certainly. I mean, I'll request the same from you. If you come across, let me know, because
Sure, we definitely.
I've been trying for the past 6 years or so. It's very difficult to get funding. If you say you want to develop something, the immediate question is, there's already open source. Why do you want to develop a new open source?
Yes.
They don't buy the idea. No, it's not Indian. So what? I mean, the counter argument, they say, so what? You can use it.
Hopefully, our government will take notice, and
yes, hopefully, yes.
And we'll obviously.
I mean, I think it should start from the institution level. People should appreciate writing your own code, at least from the academic. Then I think it will slowly penetrate to higher level up. I mean, there are two ways to look at it. Either the push could be from the government and said, okay, everybody should write your own code, only then you'll be funded.
Yes.
And also, we've seen from the institute appreciate the small work that students develop, which can then be taken up and say, okay, we have this, give us funding so we can move large scale.
Yeah, hoping for the best. And so I think it was a wonderful discussion, and it was a wonderful talk. Thank you, Dr. Sundar, for taking out 2 hours from your busy schedule. And
I'm sorry it took more time than what was allotted to me.
No, it is absolutely fine.
It always happens when I start talking about these techniques. Somehow, I mean, in fact, I have another 40 slides or so, but didn't want to bore you guys with other details.
No, it is perfectly fine. But it was I personally enjoyed the talk, and I got to know about so many things which I didn't know before this talk. And I hope the participants also share the same feeling. So we look forward to have future collaborations with you. I hope the faculty members would also communicate to explore the to all the collaborations with you and the other faculty members of IIT Madras. So with this, I would like to thank you again, and I would stop the recording now. So.